Yes, okay. So today's speaker is Dr. Xie Bao from Waseda University, Japan. And she will be talking about the quantum computing-based optimization method for a multi-day travel recommendation. So it's a kind of the application with this quantum annealing machine. So I hope all the participants will be enjoying her talk. Okay, so about please start your seminar and 20 minutes talk and 10 minutes discussion. Yes, roughly. Yes. Okay, please start.
Okay. So thank you, Dr. Kawabata, for your kind introduction for me. So I'm Sia. I'm currently an assistant professor at Waseda University. So in the next 20 minutes, I would like to give a seminar with the title "A Quantum Computing-Based Optimization Method for Multi-Day Travel Recommendation." Also, I would like to especially thank Professor Tawada and Professor Togawa from Waseda University and Professor Tanaka from Keio University who contributed to the study a lot. And also I would like to thank Dr. Warburton for inviting me to this seminar today. So in this study, we focus on a problem called the multi-day travel planning problem, also called as MTPP. As you may tell from the name of the problem, it's kind of a routing problem. So we can consider the MTPP is a generation of the traveling salesman problem. So in the no more traveling salesman problem, well, given a bunch of POIs A, B, C, D, we assume we start from the point B and we visit the rest of the POIs C, D, A one by one, and finally we return to the B. And also the route among the A, B, C, D should be the shortest. So by consideration, based on the consideration of TSP, so we can see that the MTPP is a large complex TSP with multiple constraints and multiple objectives in the real world. For the constraint in the real world, for example, like the traffic flow is different from time to time. Well, you may know that in Tokyo recently, the traffic is pretty bad around 7 a.m. to 8 a.m. So it is kind of important to decide how many times you're gonna spend on visiting the POIs and how many time you're gonna spend on moving from POIs to POIs. Well, unfortunately, our NP hard problem like TSP for using the conventional computers, it seems impossible to find the optimal solution within a realistic time limitation. However, the good news is quantum machines such as D-wave system, a quantum-inspired machine developed by physicists Hitachi and Fixed Star, those machines are designed to effectively solve those complex optimization problems. In other ways, what the word effectively means those machines can find the optimal solution very, very fast. So the theory behind those machines is composed of two main parts. The first part is transform the key elements of the problem to the suitable models, and those models are called the Ising models. Well, this model can be considered as the directed graph with many nodes, and these nodes are called spin with two values, -1 and +1. So if the spin value is +1, it means the direction is up. If the spin value is -1, it means spin is direction is down. Also, you can see here is some notation like J something. It is the coupling constant between two spins. Well, for example, the J12, it means the coupling constant between the spin number 1 and spin number 2. Well, if the two spin directions are the same, so 1, 1 or -1, -1, so the coupling constant are positive. Well, if the two spin directions are different, like 1, -1 or -1, 1, so the coupling constant are negative. Well, this kind of model can also be represented in the form of energy function like here. So after constructing an energy function of the Ising model, we start from random state, an interstate here, and we gently and slowly decrease the temperature and the quantum fluctuation until the ground state is reached. The ground state here means the state with the minimal value of H here. So if we reach the ground state, we can see that the ground state is the optimal solution to the original problem. As I mentioned before, the MTPP can be considered as a generation of TSP. So we can solve the MTPP in the same way we deal with the TSP, like solve the whole problem by one step. It's a one-phase optimization. Also, on the other hand, we can also use the concept of clustering first and routing later. So it means in the clustering phase, we would like to decide which POI and how many POIs we would like to visit each day. So several clusters could be generated. So and after generating several clusters, we solve the routing problem in each cluster one by one. Well, by searching its shortest road around among those POIs, and we connect those subroutes one by one. So here we can have the complete roadmap here. So firstly, I would like to introduce the one-phase optimization here. Here, in the one-phase optimization, we consider constraints with four constraints. The first one is each POI should not be visited more than once. And second one is user must not visit two POIs at the same time. The second one is user must not stay or start at two hotels at the same time. The last one is, well, the total travel time should never go beyond the time limitation. And here it is important to note that this one, the first constraints, well, if we are dealing with the no more TSP, so all the POIs should be visited exactly once. However, we are dealing with the traveling planning problem. So it means that only like maybe 10% or 20% of POIs should be visited, and the rest of the POIs should be allowed not to be visited. So for the first constraint here, if we are dealing with the TSP problem, the constraint should be rewrite as like each POI should be visited exactly once. However, now we are dealing with a traveling problem. So the description of the first constraint is like each POI should not be visited more than once. And here we consider two objectives in this problem. The first one is maximize the sum of certification over POIs for sightseeing. And this objective aims to help users visit all the interesting POIs as many as possible. And for the second one, it is to minimize the travel cost. Well, obviously, this objective aims to help users save their money as much as possible. So here, and the next step is to transform these four constraints and two objectives into Ising model. However, instead of using Ising model, we use a model called the QUBO model, which is equivalent to the Ising model. And for the QUBO model, we define two binary variables here. The first one binary variable is xijk. Well, it is designed in a three-dimensional model. And for this binary variable x, it is designed to decide which POI should be visited each day in what kind of order. So like if the ixijk is 1, it means to visit the POIK at I day in the j's place. Oh, if it equals to 0, it means not to do that. Likewise, for the binary variable like y here, this binary variable decide which hotel should be stay at the end of the day. If the yik is 1, it means at Hotel K at the end of day I. Otherwise, it means do not to stay at that hotel. Also here are the detailed representation of object 1, 2, and the constraint 1, 2, 4 here. Well, if you would like to have some detailed explanation on those 5 equations, you can check my paper here. It is published in 2021 on the conference called ITSC here. Also, you may find the detailed explanation of the cube topology on this paper. So, well, after we constructing those 5 cube models, we can like merge those 5 models into one big energy function H. And for each objective and constraint, a unique hyperparameter called lambda is assigned to each of them. And the each lambda is positive value, and it should be decided manually. For the next, I would like to share some experimental results here. First, we use dataset for the evaluation. The first one is Sapporo. Well, here you can see it's a southern city is in the southern part of Japan. And for the Tokyo, I guess all of you are quite familiar with Tokyo. Okay, so it's around here. And for the 5 hyperparameters in each data set, as you can see here, Tokyo has more POIs than POIs in Sapporo. So for here, for the hyperparameter alpha to gamma, we set all the same. And for the hyperparameter delta, we set it a little bit smaller in Tokyo than it in Sapporo. For the machine we use for the evaluation experiment, it is called Fujitsu Digital Annealer Generation 2. Well, to know that it's not a quantum machine, it's kind of quantum-inspired machine, but it is allowed to like embed a quite big QUBO model with size over 8,000 spins, so it is suitable for solving the MTPP problems. And you can see here, and the spin required in Sapporo is around 1,000, and the spin required in Tokyo is around 1 and 600. Here are 2 like environment settings parameters for the Fujitsu Digital Annealer. So if you would like to know what actually these 2 parameters means, you may check the paper here. It's written by some physics guys here. If you would like to have more explanation on these 2 parameters, please check this paper here. So here we come to the result comparison part. We compare our method with 2 baseline methods in solution quality and computation time. The baseline one is kind of simple method. It random selects several POIs and search for the shortest road among them. The baseline 2 is a heuristic method based on here, the reference one here. So first look at the POI satisfaction and the travel cost. It is obviously that our method can obtain higher satisfaction and less travel expense, no matter in Tokyo or Sapporo. And here, the probability we either in Sapporo and Tokyo, our method achieved a 100% value, which means no constraint violation occurred in our method here. So we can have conclusions that our proposed method obtains better solution compared with 2 baselines. Well, to know that the time here, as Tokyo has more POIs, so it required more spins. So it is obviously that this time cost should be a little bit longer than the time in Sapporo here. So it's around like 2 times here for the difference between the Tokyo and Sapporo. And here are 2 examples of how actually a route look like in the real world map here. Here is Sapporo and here's Tokyo. Well, as from those two maps, you can see that route in day 3 are kind of messy here. But for the day 1 and day 2 route in day 1 and day 2, they still look pretty fine to me. So I guess I still can see the one-phase optimization method still works fine for the MTPP. Okay, that's all for the one-phase optimization measures. So next, I would like to introduce a little bit more on the two-phase optimization method here. As I mentioned before, the two-phase optimization method is based on concept of clustering first and routing later. Well, here you might ask that as you have shown in the previous slide, the one-phase optimization method seems to be effective for the MTPP. So why do we need two-phase optimization method? So I like to see the answer to this why question may be that, as you can see in the one-phase optimization, only two objectives and 4 constraints are considered. So the cube size won't be that big, be that kind of large. However, if you would like to include more objectives and constraints at the same time, the cube model might go beyond the size of cube model might go beyond the number of spins available. As you might know, the current spins on the quantum machine available recently is quite limited. So if we would like to solve the spin issue, so it is kind of straightforward to divide a large cube problem into 2 or 3 cube models and solve them one by one. So by doing this with those small cube models, the number of things required won't go beyond the size of spins available currently. And here we summarize the difference between the two-phase and the one-phase here. So for the main difference between the two-phase and one-phase is here, we consider the transportation part into the two-phase here, the fees, and how should we go from here to here by foot, by car, or by a bus. And also the must-visit POI are also considered in the two-phase method. It means if user would like to go to some specific POIs, then we can accomplish that. And also for another difference between these two methods is the number of POIs to visit each day is flexible in two-phase. However, the number of POIs to visit each day is fixed in one-phase method. It means in one-phase method, it here, if we would like to say like P here, would like to have P like 5. So it means for day 1, day 2, day 3, you gonna visit 5 POIs each. However, if we set this number of POIs to be flexible, then user can visit 3 POIs on day 1, and 4 POIs on day 2, and 3 POIs on day 3. So it's kind of flexible for user to choose what they would like to do. So here, and I would like to introduce a little bit more about these two-phase constructions. For the first phase, POI clustering, we have 3 objectives included. So the first one is minimize the POI distance in each clusters. Well, this objective aims to have all the POIs in each cluster close enough to each other. By doing this, like the messy route in day 3 won't happen in the two-phase optimization method. And continually, the object HB and HC are the same with objectives in the one-phase optimization method. And for the constraint here, we also consider 4 constraints in the first phase. The first one is should not visit more than once. It is same as the constraint in one-phase optimization. And the second constraint is POIX must be visited. So here is an example of how actually route in two-phase looks like. And we can see if user would like to visit 3, 5, and 7. So we should include those 3 POIs in the final result here. And from this example here, we successfully including those must-visit POIs in our final results. So let's go back to the constraint here. So for the second constraint here, well, duration of each day should not excess the limit. And this is kind of simple. Let's skip it. And for the last constraint here is number of POIs tends to be flexible. So actually the flexible means the word inequality, right? So however, as most of the quantum machine or quantum inspired machine only allows equation as input. So what we're gonna do is to transform this kind of inequality constraint into an equation like this one. So by doing it, no more accelerated spins are needed, and we can smoothly transform those model onto the Ising machine. Okay, so by doing the clustering phase, we can have several clusters here. And in the second phase, we would like to conduct routing searching in each cluster one by one. So the first objective here is here, as the cost over POI has already been considered in the first phase. So in the second phase, only the cost over transportation, the hotels shall be considered. And for the constraint in second phase, the total one is about time. The total time should not go beyond the time limitation each day. And the second constraint is start and at a hotel for each day. However, here it is important to note that user can stay and at the same hotel. Also, user can start and end at a different hotel. Well, it's all depend on user's selections. And for the third constraint here, transportation option for our Sapporo should be exactly 1. So use this figure as an example here. If user would like to travel from here, number 14 to number POI 33, user should decide either transform from here to here on foot or move from here to here by a bus or by a car. And for the last constraint in the second phase here, it's equivalent to the constraint in the normal TSP, which means like visit all the POIs in each cluster exactly once. So it's kind of simple to accomplish, so we ignore it. So here, also we would like to introduce some comparison results for the two-phase optimization here. All the best values are labeled in red here, and so obviously our proposed method can obtain better values than the normal simulated annealing assay. And also for the annealing time part, we can see here our methods are pretty faster compared with the assay. So here we can have a conclusion that it is possible to represent complex real-world constraint objectives by using the two-phase optimization algorithms. And also, well, not only our proposed method can obtain better solutions than SA, but also our method speed up the annealing speed by 1 or 2 digits. So here. So that's all for the introduction for one-phase optimization and two-phase optimization. So at last, I would like to have a quick conclusion of the seminar today. So the first part is we introduce several quantum computing-based methods for solving the MTPP with many real-world concerns like travel expense, POI satisfaction, transportation selection, must with the POI, and etc. And for the second part, main part for the seminar today is that we show some kind of example of how to smoothly transform the key elements in the MTPP onto the QUBO model for quantum machines. And here we propose two kind of optimization strategies. For the first one phase, if the constraint objective numbers are not that kind of many. Maybe one phase will be enough, totally enough for solving the MTPP with small size or with less number of smaller numbers of constraint objectives. However, if you would like to include more constraint objectives, it is better to use like two-phase optimization instead of using one. So, okay, so also at last, and according to the experiment, it results that it shows that our method can outperform the two baselines either in solution quality and the computation time, which means our two methods are kind of effective for solving the MTPP. And I would like to continue our study in the future by like evaluating more cities and increase the number of POIs to confirm the effectiveness of our proposed method. So that's all for the seminar today. If you have any questions or comments, you can send them to the email here. And thank you all for coming today, and thank you for listening very much. That's all. Thank you.
Thank you. Thank you very much. Yeah, so it's quite interesting data and the result, and you show that there are some advantage of this Ising machine, Fujitsu data annealer, over the conventional estimated annealing. It's quite interesting. So now the session is open for discussion and question. Do you have any question or comment? Yes, Paul, please.
Yeah, please.
Thank you very much, Sia, for a very nice presentation. I guess most of my questions are about the Fujitsu annealer that you have been using. Maybe firstly, could you comment on the degree of the coupling graph? So you have these quadratic interaction terms, I guess, that you put on your digital annealer. Do all spins connect to all other spins, or is there some restricted order of the graph like with the D-wave machine?
Sorry, could you please repeat your question? I can't kind of have some noise here, sorry.
Yeah, I seem to be having some difficulties with my Zoom this morning. Apologies for that. So on the Fujitsu machine, there is an interaction graph, which is a map of spins are directly connected to which other spins. Is that a complete, or is it a graph with each spin only directly coupled to a subset of all possible other spins? So what is the interaction graph on the Fujitsu machine? That's my question.
I think it is based on completed graph here for the Fujitsu.
Okay, so I guess that's very different from the D-wave machine, which is currently restricted.
So I think that the Fujitsu digital annealer is a kind of all-to-all coupling type hardware. So yes.
Good, understood. And I guess my second question about the hardware. So I guess I saw a benchmark against simulated annealing in your presentation, which is good to see. But I guess
maybe here.
Yeah, sure. So this is nice, but I guess if I were a computer scientist, I would want to see some kind of scaling. So I wondered whether if you scale your problem with respect to the number of points of interest, for example, whether the scaling of the Fujitsu machine is similar to the scaling of simulated annealing or not.
Okay. Yeah. Scaling. Oh yeah, scaling between these two kind of methods are quite different. And actually the parameters of Fujitsu they have two kind of mode. It's like expert mode and the replicate mode. And for the expert mode, we have to decide the temperature and the decay one by one. And for the other one, it is automatically decided by the physics machine itself. So actually, I don't know how they decide those parameters. It actually is automatically decided by the machine. So I cannot control the scaling between the assay and our method are completely the same.
But have you done experiments where you change the number of points of interest and see how the computation time varies as a function of the number of points of interest? And then compare, I mean, that's what I'd like to see, I guess, is a comparison between simulated annealing and the Fujitsu annealer as you change the number of points of interest. That would be an interesting comparison.
Okay. So far I only conducted experiment on Sapporo. So actually the number of POIs are to be fixed. Okay. So I'm sorry for that. So okay. That's here the slides, only the result I can provide it to you.
Okay, fine.
Good.
Thank you very much.
Yes. Okay, so the scaling, I also have the same question. Actually, that the scaling is quite important. See the actual advantage of the such kind of the Ising-machine. Yes, so you can perform the computation using the small size problem, using small size problem. Yes, up to the this for instance the some. Yes, so then maybe you can check some scaling. Yes, so it's quite important to see. Yes. So any other question? Yes, Bruno. Yes, please. Yes.
Hi, thank you very much for the presentation. Very interesting. I was wondering, how much does the model depend on the hyperparameters, lambda, or the other ones, and how do you optimize them?
Okay, so here. Okay, so sorry. Ready? Sorry, I missed the slide here. Okay, for this one, actually the reason why I said them to be different is that actually the duration time in Tokyo is a little bit longer than the duration of POIs in Sapporo. So actually, I lowered the weight of like traveling times in the Tokyo. So as you mentioned, the setting of hyperparameters is kind of difficult to control. So actually what we is doing now is we try like 100 set of combination of the hyperparameters and we select the best of them. So far it's the only way to control the hyperparameters. I'm sorry for that.
Okay, no, I was asking because I'm doing different kind of problems, but I also have hyperparameters to optimize, and I do the same. But I was wondering if someone had a better procedure to optimize.
Yeah.
Cool. Thank you.
Well, maybe as I showed here. Sorry. So like the fixed stars, have you ever heard of it? It's a Japanese company. Like the fixed stars, if using fixed stars to amplify like annealing machine, they actually the hyperparameters they can decide by the machine itself. I don't know how do they accomplish that, but it's very helpful for the developer. Like if you are interested in like hyperparameter settings, maybe you can try this one.
Okay, I'll have a look. Thank you very much.
So, okay, good. So any other short comment? Okay, actually I have many questions, but okay, it's time to stop today's INQA seminar. So thank you very much here. So it's quite interesting talk, so I really enjoyed. So okay, so let's thanks to the speaker again. And okay, see you next. Yes. So thank you, Shia-san, Bao-san. Okay, see you next. So okay, bye.
Oh, thank you so much. Bye.